As we move into Unit 3 with Section 5.1, we're going to shift our focus away from graphing, which some of you will appreciate. Not everybody loves graphing, I know. And we're going to start focusing on our identities. Now, this is finally where you're going to definitely need to have on hand this identity sheet. For this Unit 3 test is when these identities will be provided for you. But I warn you, that's not going to help as much as it sounds like it's going to unless you have done the practice so that you're comfortable with using them and where to find the different identities as you need them. Okay. An identity is an equation that is satisfied by every value in the domain of the variable. So every value in the domain of the variable. Now, we have already gone through and studied these fundamental identities. These should all be familiar to you. But we're going to go ahead and write them down again, because the more you see them, the more you use them, the more comfortable you get with them. So for our fundamental trig identities, we have our reciprocal identities. Cotangent and tangent are reciprocals. Secant is the reciprocal of cosine, and cosecant is the reciprocal of sine. Whenever I'm writing my identities, I don't drop the argument. I sometimes get lazy with how I read them. I don't say cotangent theta is the reciprocal of tangent theta. But when I write the identity, I always write the argument. If you don't, it's just not mathematically correct. It will be counted wrong. So make sure that you pay attention to whether they're using theta or alpha or x for their argument. That angle, that input that we need to have represented on our paper. All right, quotient identities. We have two quotient identities. Tangent is y over x. We can also think of it as sine theta over cosine theta. Cotangent is the reciprocal of tangent, so it's going to be cosine theta over sine theta. Sine theta. It looks like STN. I was going to try to avoid reaching for my whiteout since this is gray paper, but we'll go ahead and reach for the whiteout. Alright, so cosine theta over sine theta. Then we have our Pythagorean identities. We took time already to develop these Pythagorean identities using x squared plus y squared equals r squared, and then we divided everything by x squared, and then we divided everything by y squared. Sine squared theta plus cosine squared theta equals 1. Then, you know what, we're going to go ahead and develop these a little bit differently. Let's come down here. If I take sine squared theta plus cosine squared theta equals 1, my primary Pythagorean identity, and I divide everything by sine squared theta, because it is a mathematically acceptable move, legal move, to divide everything by the same value. Anything over itself is 1. Cosine over sine is cotangent, so cosine square over sine square is cotangent square theta. And then my reciprocal of sine is cosecant, so the reciprocal of sine square is cosecant square. So that is this one right here. Cosecant square theta. Excuse me. And then if I started with my primary Pythagorean identity, sine square theta plus cosine square theta equals 1, and this time I divide everything by cosine square theta, sine over cosine is tangent, so sine square over cosine square is tangent square theta. Anything over itself is 1, and the reciprocal of cosine is secant, so the reciprocal of cosine square is secant square. So right there, that's the other term, the missing term from our other Pythagorean identity. So we have 3 Pythagorean identities. We think of this one as being the primary one, and these two are derived from this primary Pythagorean identity. This primary Pythagorean identity is derived by taking x squared plus y squared equals r squared and dividing everything by r squared. X over r is cosine. Sorry, I'm out of order. X over r is cosine, so that would be cosine squared. Y over r is sine, so that would be sine squared, and anything over itself is 1. All right, our negative angle identities. This is our even-odd function identity list. Okay? Even or odd functions. Hopefully you remember that cosine and its reciprocal secant are even functions. So if I plug in a negative argument, nothing changes. So cosine of negative theta is just cosine theta. Secant of negative theta is just secant theta. My other 4 trig functions are odd. So that if I plug in a negative argument, I can think of that as the opposite of sine theta. Same for cosecant, I get the opposite of cosecant theta. Tangent and cotangent, also odd functions. Tangent of the opposite of theta is a negative, or the opposite of tangent theta. Same for cotangent. So when I'm looking at my 6 trig functions, only cosine and its reciprocal secant are even. The other 4 trig functions are odd. Okay. We've already mentioned this as well. We will also use alternative forms of the fundamental identities. For example, the 2 other forms of cosine, or my primary Pythagorean identity. If I solve it for sine square, I move that cosine over and I have 1 minus cosine square theta. If I solve for cosine square theta, I move that sine square over and I have cosine square theta is 1 minus sine square theta. I can take my other 2 and I can rearrange those terms the same way. And I know we've already talked about this. I could rewrite this as cosecant square theta minus cotangent square theta is 1. I could rewrite it as cotangent square theta is cosecant square theta minus 1, because I just move a term around here and a term around there. So there are always going to be alternative forms of the fundamental identities. As we're using our identities to verify things, you're going to be looking for these things that pair up. Tangent square and secant square paired up. Cotangent square and cosecant square paired up. Sine square and cosine square paired up. Okay. Now we are going to talk about using some of these fundamental identities. We're going to make use of our fundamental identities to find function values. Cosine theta is 5/8, and theta is in quadrant 4. So let's think about quadrant 4. Quadrant 4 is down here. Cosine is positive, sine is negative in quadrant 4. I know that cosine theta is 5/8. I need to find sine, tangent, and secant of the opposite of theta, negative theta. Well, I've got cosine, I need sine, I want to use Pythagorean, I want to use my fundamental identities. I have alternate ways to solve this. I could put that on a graph because cosine is x over r. I can set it up as an angle in standard position and solve for y, and then use those 3 values. But since I'm being told to use my fundamental identities here, I want to think, okay, well, I've got cosine, I need sine. Those are used, both of those are used in cosine square theta plus sine square theta equals 1, my primary Pythagorean identity. I know cosine, so let's fill that in. 5/8 squared plus sine square theta equals 1. We're going to solve for sine square theta. So I need to square this, and I need to move it over and subtract it from 1. Well, when I square this, I get 25 over 64. I need to subtract it over here, so when I move it over to subtract it, I need a common denominator. I'm going to rewrite 1 as 64 64ths. We said when we squared this, we get 25 64ths. so that I end up with sine square theta is equal to, well, 64 minus 25 is 39/64. Now I've solved for sine squared, but I haven't solved for sine. To finish solving for sine, I take the square root of both sides. Now when I take the square root, I consider plus or minus, but I've already been told that I'm in quadrant 4, so I know that my sine function value is going to be negative. So the square root of sine squared is just sine theta. I know this is going to be negative. Square root 39 does not simplify, but the square root of 64 is 8 because we did 8 squared to get 64. So that is going to simplify to negative square root 39 over 8. That's my sine function value for this angle in quadrant 4. Okay, we're challenged. We've got multiple ways to set this up and work it, but we are told to use tangent theta. We're finding tangent theta. We're told to use our fundamental identities. Well, one of our fundamental identities is that quotient identity. Tangent is sine over cosine. So we're going to use that quotient identity, sine theta over cosine theta, because we know both of these values now. Sine theta is a negative square root 39 over 8. Cosine is a positive 8, or excuse me, a positive 5 over 8. I was given that value. I'm dividing with fractions, so I'm going to multiply by the reciprocal. When I multiply by the reciprocal, that denominator is what switches upside down. Those 8's are going to cancel out, and my value for tangent of this function is a negative square root 39 over 5. Alright, last one, secant of a negative theta. Well, secant is the reciprocal of cosine. Secant is 1 over cosine, so we're going to be 1 over cosine of a negative theta. Is cosine an even function or an odd function? Remember that cosine and secant are even functions. So the cosine of a negative theta is going to be the same thing as the cosine theta. And I know cosine theta. Cosine theta is 5/8. The reciprocal of that is going to be 8/5. All right, excellent. Let's practice one more time because getting the hang of this can be tricky at first. We have a tangent function value. We're told that our angle is in quadrant 2. Quadrant 2 is over here. In quadrant 2, x is negative, y is positive. That makes sense. Tangent is negative, so we're in good shape. I've been given tangent and asked to find secant, so I'm going to, by using my fundamental identities. When I look at my fundamental identity list, I see that tangent and secant are paired together in the second of my Pythagorean identities. So I'm going to be using the identity tangent square theta plus 1 is equal to secant squared theta. And I'm going to plug in what I was given. Negative 5/3 squared plus 1 is equal to secant square theta. When I square this, I get a positive 25/9. I need to add 1 to that. So I'm going to rewrite my 1 as 9 over 9 because when I add or subtract fractions, I need that common denominator, right? So I've got 34/9 is equal to secant square theta. And once more, I need to solve for secant by taking the square root of both sides. Now, when I take the square root to solve for an unknown, I have to consider plus or minus, but I know that I'm in quadrant 2, and secant, because it's the reciprocal of cosine, is going to be negative in quadrant 2. So since I know what quadrant I'm in, instead of having to do the plus minus, I can narrow it down and say, okay, it's going to be negative. So my value for secant theta is going to be the negative square root of 34 over 9 is a perfect square. So negative 34/3. Alright, next function I'm asked for is sine theta. I know tangent, I need sine. The two of these are tied together in my reciprocal identity for tangent. So let's just use that again. Tangent theta is equal to sine theta over cosine theta. Now secant theta is the reciprocal of cosine, correct? So cosine theta would be a negative 3 over square root 34. Now we're not going to leave it like that as an answer, but we can use it like that and not work on doing the rationalization until we know we're ready to do that. Okay, so tangent theta is a negative 5/3. We don't know sine, that's what we're looking for. Cosine theta is going to be a negative 3 over square root 34. To solve for sine square, or for sine theta, I'm going to multiply both sides by that denominator. Negative 3 over square root 34. Negative 3 over square root 34. Negative times a negative is a positive, and that works for me because we're solving for sine, and sine is positive in quadrant 2. Those 3's are going to cancel out, so I'm left with 5 over square root 34 as my value sine theta. Now this is going to be my answer, so I do need to rationalize here. When I rationalize, I end up with 5 square root 34 over 34. Okay. Looking at this final identity, what do I know? Well, I've got cotangent. I know that cotangent and tangent are odd functions, not even. So that's going to be equal to the opposite of cotangent theta. And cotangent is the reciprocal of tangent, so that's the opposite of 1 over tangent, not 1 over 1, just 1 over tangent theta. Sorry, I got to talking and writing and I got ahead of myself. 1 over tangent theta. And I was given tangent theta, so I can use this given. So 1 over a negative 1 over a negative 5/3. A negative times a negative is a positive. I take the reciprocal of that and I end up with a positive 3/5. Alright, excellent. Now, to avoid a common error, when you're taking the square root, be sure to choose that algebraic sign based on the quadrant of theta and the function being evaluated. That's why I took a second with both of these to do just a super quick sketch to see what I'm looking at. Don't skip the sketch. Don't skip the sketch. That knowing which quadrant you're in, having a visual of that, and having thought that through before you attack your problem will save you grief later on. It'll save you missed problems. Alright, let's look at this next page. We're going to start working with identities. There's some things you need to know. There are multiple approaches to working with identities. For those of us who are very linear thinkers, and once we see one way forward, that's the way we're going to use, by golly, this is a struggle for. It's also a struggle because we typically, until we get comfortable doing math, we want to have a way forward before we start. When you're working to verify identities, you don't always know what's going to work. So when you don't know where you start, where you need to start, just start somewhere. Try something. See where it takes you. If you don't like where it takes you, then you go, okay, well that didn't work, and you go back and you try something else. I'm going to be giving you tools for a toolkit here. Ways to start, different things to try to work with these identities. When you're working to figure out what to try, you want to find connections among the functions. For example, on that last one, we were using our fundamental identities, and so I looked at what we were given and what we needed. When we were given tangent, we needed secant, I pulled out this identity. When we were given sine, we needed cosine, I pulled out this identity. When we were looking for tangent and we had sine, I pulled out my reciprocal identity. So you look for connections among the functions, and you want to manipulate the functions arithmetically. Your rules for math still apply. You can only make mathematically legal moves. You can multiply if you can simplify, you can factor. If you have an equation, you can multiply or divide both sides of the equation by the same value. But if it's not something you can legally do mathematically, you can't do it with your identities. Okay. We're going to write one trig function in the terms of another. Now notice that we are not solving anything. We're not finding a value for theta. We're taking one trig function and we are rewriting it in terms of another trig function. This is, a lot of the time, this turns out to be messier than it starts. I have tangent theta and I want to end up in cosine theta. I have tangent theta and I want to end up in cosine theta. So I have one trig function. I want to end up in just cosine. There are multiple ways to do this. I'm going to show you two. The first example that I'm going to show you, I say, okay, well, I don't have a tie between tangent and cosine, but one of my trig functions is tangent square theta. One of my Pythagorean identities is tangent square theta plus 1 is equal to secant square theta. And I know that secant ties to cosine because secant and cosine are reciprocals. So I can say, all right, that gives me tangent square theta plus 1 is equal to 1 over cosine square theta. And let's move that 1 over. So tangent square theta equals 1 over cosine square theta minus 1. And remember, when we subtract fractions, we need the denominators to be the same. So I'm going to rewrite my 1. That minus 1 comes over here. I'm going to rewrite it as cosine square theta over cosine square theta. So I can write this as a single term. So I'm solving for tangent square theta. I moved that 1 over by subtracting it, and when I subtracted it, I wrote it as, this is my well-chosen 1. Anything over itself is 1. Now I have a common denominator here, so I can say, all right, tangent square theta is 1 minus cosine square theta all over cosine square theta. Now we wanted to rewrite tangent in terms of just cosine, so let's solve for tangent and see what it looks like in terms of cosine. If I take the square root of both sides, now I don't have a specific quadrant, so I do have to have plus or minus. The square root of tangent square is just tangent theta, so there's my tangent theta, and that's going to be equal to, well, my numerator over here, plus or minus square root of 1 minus cosine square theta. We're going to leave that alone, but the square root of cosine square theta is just cosine theta. So I started with making a connection between the two functions that I was interested in, and then I got it down to a point where I could say, okay, tangent theta is the same thing as all of this. Plus or minus, because I don't know what quadrant I'm interested in, square root of 1 minus cosine square theta over cosine theta. That's the only trig function that I have. Just cosine, and that was my charge, was to put tangent in terms of cosine. Okay, let's look at another way to do this, a second option on how to approach this. Well, I also know that tangent theta, according to the reciprocal identities, is sine theta over cosine theta. Those two things are the same. If I square both sides of my function, I would get, because squaring both sides, raising both sides to the same power, multiplying both sides by the same constant, dividing by the same thing, those are all legal moves mathematically. If I square both sides, that would get me to tangent square theta equals sine square theta over cosine square theta. And my fundamental, that first Pythagorean identity, sine square theta plus cosine square theta equals 1. Well, I can solve that for sine square theta. That is 1 minus cosine square theta. If I rearrange terms for that first Pythagorean identity, I get that sine square theta is the same thing as 1 minus cosine square theta. So I can do a substitution there. So now I'm to tangent squared theta is equal to 1 minus cosine squared theta over cosine squared theta, because I did a substitution using that Pythagorean identity. And then I'm to this last step that I did over here, where I said, okay, well, I need to know what tangent theta, not tangent square theta was, so that I have tangent theta is equal to plus or minus square root of 1 minus cosine squared theta over cosine theta. Same result. I've got the same value for tangent theta in terms of cosine. I just approached it a different way. Now you're probably sitting there going, oh my gosh, where did she come up with that? Where did that come from? Well, it came from trial and error and working with these problems until I found connections among the functions. This is not something that you are just going to sit down and magically do, because it's not a, oh, here, remember these 3 steps. This is what you're doing every time. This is getting familiar with the concepts, understanding how the identities work together. As you move through Trig, you are leveling up mathematically. You're moving to a level where you really have to understand the concepts mathematically and how you can use them to do things, to move you ahead without just memorizing algorithms, memorizing steps. All right, cosine x. We want to rewrite cosine x in terms of tangent x. Once again, I'm going to do this a couple of different ways. We want to rewrite cosine x in terms of tangent x. Now, I've been given an argument of x. Last time I was given an argument of theta. This time I have an argument of x, so when I write my identities, I need to use x as my argument. Well, tangent and cosine, I'm working back the other direction. So, but I've got the same, I'm going to start with that same link. I'm going to start with that same Pythagorean identity, tangent square not theta. I just said that and then I wrote it down as the wrong value. Tangent square x plus 1 equals secant square x as my argument. Don't drop off the x, don't leave the argument off. Make sure you use the argument you were given. Alright, secant, reciprocal of secant is cosine. That's the link we need to make. So we've got 1 over cosine square x. I'm going to rearrange my terms. I'm going to multiply both sides by this denominator, cosine square x. So now 1 is equal to cosine square x times tangent square x plus 1. And solve for cosine square x by dividing out the tangent square x plus 1. So I'm dividing out, I'm just rearranging terms. That's all I've done here is rearrange terms. So I've got cosine square x on one side equals 1 over tangent square x plus 1 on the other side. I'm nearly there writing cosine in terms of tangent. The only thing I still need to do is take the square root. When I take the square root, I have to remember plus or minus. So cosine x is equal to, well, the square root of 1 is 1. So I've got plus or minus 1 over square root of tangent square x plus 1. I'm done, except I need to rationalize that denominator. When I multiply it by that well-chosen 1, this square root over itself, I end up with plus or minus square root of tangent square x plus 1 over tangent square x plus 1. So that is writing cosine x in terms of tangent x. So I promised you a second approach to this, a second way to try. Starting in the same place though, because that's my link between the two functions. Tangent square x plus 1 equals secant square x is my Pythagorean identity that I'm using. I am going to take the reciprocal of both sides. That's another legal move mathematically that we don't think about a lot. I'm going to take the reciprocal of both sides. When I do that, they flip. So I end up with 1 over tangent square x plus 1 is equal to 1 over secant square x. Well, 1 over secant square x is cosine square x. So I've got 1 over tangent square x plus 1 equals cosine square x. This is that step right there. And the rest of it is going to be identical. I just take the square root of both sides, consider plus or minus 1 over that square root. And then I need to rationalize my denominator, and I get to that same spot. So no matter which approach I take, I end up at the same point. But there's more than one way to get there. And these are just the two ways I saw. You might approach it differently and still get to that correct answer. All right, one last page of this section of notes. We are rewriting an expression in terms of sine or cosine. This is another tool for my toolbox. I can rewrite things in terms of sine and cosine. And then I'm going to simplify the expression so that no quotients are going to appear. Quotients are division problems. So right here I've got a quotient. I want to end up with an expression, not an equation. I'm not solving anything. I'm just rearranging things without a quotient, a division bar. Okay. First, I'm going to put everything in terms of sine and cosine. So my numerator of this big rational expression becomes 1 plus, well, tangent square theta is sine square theta over cosine square theta. My denominator, 1 minus, and secant square theta is the reciprocal of cosine square theta. Now I see that I have a big fraction, a big division problem, numerator over denominator, and then within my numerator and my denominator, I have a smaller denominator, right? I've got little rational expressions inside my big rational expression. So up here I have a denominator of cosine square theta. Down here I have a denominator of cosine square theta. I can simplify this by multiplying by that well-chosen 1, multiplying cosine square theta into both my numerator and denominator. So here's what happens. When I multiply cosine square theta into my numerator, goes to both of those terms, cosine square theta times 1 is cosine square theta. Cosine square theta times sine square theta over cosine square theta. Well, what does that look like? I'm going to do some little side work up here. I've got sine square theta over cosine square theta. I'm multiplying that by cosine square theta. That cancels, and I'm left with plus sine square theta. By multiplying the numerator and denominator of the whole thing by that little interior denominator, I cleared out that little fraction that's inside my big fraction, my big rational expression. Same thing's going to happen in the denominator where I multiply, I distribute this cosine square theta to both terms. Cosine square theta times 1 minus, and this becomes cosine square theta over cosine square theta, which is just 1. Alright, so I want to end up with no quotients. I've still got a quotient. So what can we do here? Well, do you recognize anything? My numerator, hopefully you're getting comfortable with this primary Pythagorean identity. Cosine square theta plus sine square theta, that's my Pythagorean identity. That is equal to 1. So that's 1 over cosine square theta minus 1. Let's see what we can do here. We just used our Pythagorean identity. Cosine square theta plus, or sine square theta plus cosine square theta equals 1. If I do cosine square theta minus 1, so I've got cosine square theta, I bring that 1 over. That means I subtracted that sine square theta over as well. So I can take my Pythagorean identity, I can rearrange the terms so that I get cosine square theta minus 1, and that is equal to a negative sine square theta. So 1 over a negative sine square theta. I still got a quotient. But this looks like a reciprocal. So what's the reciprocal of sine? Reciprocal of sine is cosecant. So the reciprocal of a negative sine square theta is a negative cosecant square theta, I have started out by taking what I was given, putting it in terms of sine and cosine theta, and then writing it so that I have no quotients. That's what I was asked to do. Make sure that you always read the instructions so that you know what you're asked to do. Let's practice one more. We're asked to do the exact same set of things. We're going to take our expression, put it in terms of sine and cosine. That's a great tool, by the way. And then simplify so that I have no quotients. I want you to pause the video and work on that, and then come back. So this problem looks a whole lot like that other problem, with the exception that my little denominator is now sine square theta. But I'm going to approach it the same way. I'm going to multiply by a well-chosen one, where I am multiplying in that little internal denominator so that I can simplify those interior fractions. Sine square theta times 1 plus sine square theta times this ratio. The sine square thetas are going to cancel, and I've got cosine square theta. In my denominator, sine square theta times 1 minus, this time, sine square theta times 1 over sine square theta is just 1. Now, you're primed and ready. You know you're looking at that Pythagorean identity, that primary Pythagorean identity. Sine square theta plus cosine square theta equals 1. That's my numerator, so my numerator is just 1. My denominator, I have sine square theta minus 1. So if I move this 1 over to get sine square theta minus 1, I've got to move that cosine square theta over to the other side of the equation. So that's going to be equal to a negative cosine square theta. That's in the denominator. That's still a quotient, so I need to use the reciprocal identity, and that gives me a negative secant square theta. I did not drop the squares. I did not drop the arguments. I kept the form of the terms all the way through. That is super, super important. I've got it here as a bullet point just to remind you. Be sure to write the argument of the function. For example, sine square theta plus cosine square theta is equal to 1. That's what it needs to look like, except probably not that messy. That looks like a fourth power. That messed up my C. Thank heavens for whiteout. Cosine square theta. Sine square theta plus cosine square theta equals 1. That's excellent. If I go to, however mysteriously, somehow, it ends up being sine square plus cosine square equals 1, that's just wrong. That's not right. That doesn't work. Don't do that. Okay? Don't leave off your arguments.